Thank you very much. Okay, let's see. Well, I want to thank my co-authors here, Gennady Chiporin, Ligan Chen, and Senya Grazi, and our collaborators, Yehenia Kalnai, who permeates everything here, and a student Kriti. So I want to say four things. I want to tell you a little bit about surface fluxes and tell you what the problem is with surface fluxes. I'm going to show you results from temperature increments from an ocean reanalysis forced by atmospheric reanalyses. And I'll propose a way to correct the problems with the fluxes, and I'll give you a fitness test so that we can evaluate how good the correction is. And then I'll talk about a few related issues like bulk formulas. So atmospheric reanalyses refine the state of the atmosphere based on a whole series of satellite and in situ observations. And surface fluxes are really the residual of the internal energy budget. And so this is an example of surface heat flux, time mean surface heat flux from the MERA-2 reanalysis. And here is a similar picture from the ERA interim reanalysis. And you'll notice comparing these two pictures that, in fact, they're rather different, and rather different at the scale of, say, 10 to 30 watts per meter squared, quite large differences. And we can understand why there are such differences, because, as I say, fluxes really are the residual to try and make the internal heat budget balance. And of course, this has been known for a long time, and there are a series of meteorological approaches to try and fix the fluxes, make better use of the atmospheric observations, include the fluxes as a parameter to try and put greater emphasis on getting the fluxes right. But in the oceanographic community, there also is a history of efforts to try and fix the surface fluxes. And these fall mostly in the category of constraint problems or inverse calculations, the most sophisticated of which was a 40 var algorithm proposed by Detlef Stammer in 2004, in which he included surface fluxes as one of the state variables of actually the ocean. And so in that way, observations in the ocean could be used to improve the calculation of surface fluxes. And so everything I'm going to tell you in this talk is really to try and do the same thing that was done with this 40 var technique, except try and do it with sequential data assimilation, and then try and present to you some physical interpretation. And yeah. So now I'd like to tell you a little bit about oceanography. And of course, an ocean general circulation model is very much like an atmospheric general circulation model. So there's an internal energy budget equation. And in fact, it's very simple. This is the equation right here, where Q is the net surface heat flux I've vertically integrated. And there are two limiting solutions to this equation. So the steady state solution just has divergence of heat transport on the left-hand side, balancing net surface heat flux. But the interesting solution for us is the high-frequency solution, in which heat flux in the ocean is really balanced just by local storage. And it's going to turn out that the heat budget for that's of relevance for sequential data assimilation is really the limited case on the right-hand side. And I point out, of course, if you're at high latitude, you have to include the heat storage in melting and freezing of sea ice as well. So it gets slightly more complicated, but I won't really talk about that. Okay, so increments, we all knew about these differences between the observations and the forecast. Again, I'm going to show you increments vertically averaged or vertically integrated. And in the same way that we can form internal energy equations for the atmosphere and the ocean, of course, it's easy enough to form an incremental energy equation. So we actually can come up with a time rate of change of the increments. And of course, on the right-hand side, we have this difference between the observed, or the maybe better stated as the true surface heat flux, and the surface heat flux actually delivered to the ocean from these atmospheric reanalyses. And just in the case of the internal energy budget for, say, the atmosphere of the ocean, there are transport terms, there's local storage terms on the left-hand side. And this equation's the whole point of, or part of the point of this talk is that this equation is going to be dominated by that term on the far left-hand side. So now let me skip to results. So I'll look at 3 different atmospheric reanalyses, ERA interim, MERA-2, and JRA-55. I'll force an ocean reanalysis system for the 8-year period from 2007 to 2014. I'll collect all these temperature increments. And now I'm showing you what the vertical profile of the time mean increments looks like for these 3 different experiments that I've described. And you'll notice that all the action is quite close to the surface. So the misfits are quite close to the surface, and they're quite large, and they're quite negative, meaning that the observations are constantly trying to cool the ocean. So the oceans are too warm. And it's quite striking. And since a lot of it's in the upper 75 meters, I want to show you what the spatial structure is. So for now on, I'll just integrate over that upper 75 meters, and I'll show you what the spatial structure of those increments looks like. Again, just for convenience, I'll just look at the time mean over this 8-year period. So each of these panels shows the spatial structure of the misfits in this ocean reanalysis system, which is ingesting on the order of 3 or 4 million vertical profiles, a lot coming from the Argos system. And the units now are watts per meter squared. And you can see what the actual misfits are as evaluated by the ocean for MERA-2, for ERA interim, and for JRA-55. And you can see that the misfits are large. In this particular case, it looks as if ERA interim's a little bit closer. We're going to see at the end of the talk, actually, that's slightly misleading. Just to give you an idea of some of the structure in here, I'll look right north of the equator in the tropical Pacific. You'll notice there's some little oscillation in there. If you kind of blow up that picture and you look just north of the equator in the tropical Pacific, and you look at this imbalance in heat, again in units of watts per meter squared, you'll see there are huge excursions. Heat coming into the ocean, heat going out of the ocean, heat coming into the ocean. This is for the ERA interim forced ocean. And the scale is, 40, 50 watts per meter squared. It's huge. And in fact, it's kind of easy if you think about it for a little bit to understand what's going on here, because these excursions are spaced 1,500 kilometers apart. And if you mention 1,500 kilometers to an oceanographer, the first thing they're going to think about is the Tau Triton mooring array, which is in the tropical Pacific. And in fact, studies of the reanalyses over the Tau Triton mooring array have actually shown that there are these substantial humidity anomalies in the ERA interim reanalysis associated with ingesting this Tau Triton mooring data. And so what we've found basically is we found evidence of this problem, not looking in the atmosphere at all, but simply looking at what the atmosphere is doing to the ocean. So this is just one example of how we can infer something about what's going on in the atmospheric reanalyses by taking a closer look at the ocean. The next thing I want to point out is that these increments that we see in the ocean actually have a very strong seasonal cycle to them. So if you just sort of average over the central North Pacific like this, and you plot the increments as a function of depth and time over the upper 300 meters, you see that there's this very strong annual cycle. And that annual cycle, of course, is linked to the change in surface temperature and the seasonal deepening and reformation of the mixed layer. So there's very strong tie to the mixed layer. These increments are basically getting distributed over the oceanic mixed layer and affecting the water down to the base of the mixed layer and affecting the stratification at the base of the mixed layer. And I'll come back to that point at the end of the talk as well. But so you can't just fix the time mean of the surface fluxes. You absolutely have to fix the seasonal cycle. So that is my explanation of the problem, that we have these errors in net surface heat flux. They're large. If you want to pick a number, you're talking about like 10 to 30 watts per meter squared. The global warming signal is about 1 watt per meter squared. So if you wanted to pick the global warming signal out of net surface heat flux, you've got to bring the errors down by more than a factor of 10. Now I propose my solution. So my solution is to infer from the ocean observations the corrections that we need to impose on the atmosphere, on the atmospheric flux. And of course, I showed you what the misfit was, so it's very easy to simply compute a seasonal cycle from those misfits and then put that back into the atmosphere. And so here it is right here, that red delta Q. And now I propose my test of the efficacy of this approach, which is that I rerun the whole system. So I've now fixed the atmosphere and atmospheric reanalysis surface fluxes. And I put that back on top of my ocean. And I repeat this ocean reanalysis. And I do this 3 different times with these 3 different surface fluxes. Okay, so if we've done things right, then the increments should look a lot smaller. If we've done things wrong, then the increments won't. And so on the left was the vertical profiles that I showed you before. On the right is what you get after you go through this correction process. And I know you don't have too much time to look at this, but if you pick out one of those curves and look at the curve on the left and look at the curve on the right, I think you'll see that they're quite a bit smaller. And I showed you the spatial picture before. So let me show you the corresponding spatial picture of the increments, as I say, integrated over the upper 75 meters for this experiment where I've fixed the surface fluxes. And so those are these panels on the right-hand side. And so where you see white, it means that the errors are within 5 watts per meter squared of, plus or minus 5 watts per meter squared. So we want to see a lot of white. And so that's reassuring. We see a lot of white. You see some red down here at high latitudes. That has to do with sea ice, so I won't talk about that. You'll notice that there's some blue along the equator here, so some misfits along the equator that don't go away, and also you'll see these western boundary current regions. And just give you a little more detail, let's show you what's going on in the western North Atlantic, where we have this very strong boundary current, the Gulf Stream. And you'll notice that there's kind of a dipole, so there's red on the eastern side of the stream, south and east of the stream, and blue north of the stream. And this is just a blow-up of the picture for the 3 different experiments, forced by MERA-2, forced by ERA, forced by JRA. And here's Newfoundland right here. There's, I think that's Greenland right there, Spain over here. And here's the Gulf Stream right in here. And there's that dipole with the blue and the red down below. And now I'll show you what happened in this region of the ocean where we fixed net surface heat flux. So now things look much better in the interior. We're within plus or minus 5 watts per meter squared, which is great. But we still have these anomalies along the western boundary current. And so then the question is, well, if these anomalies are not being caused by errors in net surface heat flux, what are causing these anomalies? And oceanographers taking a look at this would probably immediately say, there's something wrong with the model, because we know that those models don't do these western boundary currents very accurately. And that is the argument I'd like to make. So I'm going to show you what a vertical section cutting across the Gulf Stream. So here's the Gulf Stream coming through right here. I'll show you that vertical section. And in schematic diagram, this is what that vertical section looks like. So there's a very strong temperature front. So vertical axis depth, horizontal axis latitude, very strong vertical front. The thermal wind gives you that very strong Gulf Stream coming out of the screen. And if we know that these ocean models, this is an eddy permitting model, those ocean models aren't so great, so they can't maintain these fronts very steep fronts, so the fronts tend to slump a little bit, so the isotherms kind of collapse a little bit. And if you think of what that means in terms of increments, it means you're going to get negative increments up here and positive increments down here. In other words, you get that dipole pattern we saw just a moment ago. And in fact, if you actually look at these sections in the model, you see exactly that, this positive, negative pattern of increments. So what we're really seeing here is not a problem with nets. This is not a problem that's coming in from the atmospheric forcing. It's actually a model deficiency. So we've now found problems with atmospheric forcing and problems with model deficiency. I have two more things to tell you, and then I'm done. So the first thing I want to tell you is that I kind of glossed over an important detail in this problem, which is that these atmospheric reanalyses produce surface variables, and the actual fluxes are calculated by bulk formulas that are built into the atmospheric general circulation models. And there's considerable uncertainty about these bulk formulas. And the bulk formulas that in everything I've shown you so far are the ones that were provided to us by GFDL, and they're actually in the GFDL coupled models. But there are alternative bulk formulas. And in fact, if you compare, so this is the one we're currently using, you compare that to what's considered the most modern version of these bulk formulas, Core 4, you'll notice that, in fact, for the same, say, 10-meter wind speed, the stresses under storm conditions for Core 4 are 10 to 20% higher. So there's considerable change in the surface stress and similar changes in latent and sensible heat flux. So all these things are quite sensitive to these bulk formulas. And so another way in which we could use these increments is to decide what's a good bulk formula. So we could take an atmospheric reanalysis, use the NCAR bulk formula, force the ocean, use Core 4, force the ocean, and see just how sensitive the misfits in the ocean are to these bulk formulas. So on the left is the picture I showed you before. On the right is the picture, exactly the same calculation, but just repeated with this different, implementing a different bulk formula. And again, there's quite a bit more white over here, suggesting that the Core 4 bulk formula is actually quite a bit more consistent with the ocean. So this gives us a mechanism for evaluating these bulk formulas. The last thing I want to tell you about are these patterns of big imbalance that you see, for example, along the equator, and they exist in coastal upwelling regions. And so Core 4 is more compatible. And we think that the origin of this really has to do with the fact that if you just integrate over the upper 75 meters, you're actually mixing together effects that are due separately to net surface heat flux errors from the atmospheric reanalyses and wind stress errors from the atmospheric reanalyses, because the ocean's quite sensitive to wind stress in upwelling zones, and the places in solid ellipses here are all upwelling zones, including the South Equatorial Indian Ocean. And so the solution is to come up with a more natural layer over which to integrate, and the natural layer is the actual mixed layer of the ocean. So if you simply replace this fixed 75-meter layer with the mixed layer, then a lot of these funny anomalies that occurred along the equator go away. And so that's really my last point. So let me just summarize what I've come up with here. And so that's my 5 minutes. Is that okay? So, so we're very interested in trying to get more accurate surface fluxes. If we were to be able to get surface flux estimates to, say, 5 watts per meter squared, and the anthropogenic signal is about 1 watt per meter squared, then that means that if we can simply accumulate our fluxes over about 10 years, we should be able to pick out that anthropogenic signal. So that would be a really great thing. And but trying to do that flux correction in a full-blown 4D VAR calculation is very difficult. So we'd like to be able to use our more convenient sequential data assimilation, and we've tried this out, and our conclusion is that it works great. It's cheap, it's iterative, so you could keep repeating this process and get more and more accurate estimates. And a few more conclusions. So in playing around with this approach, we found that, as I said right at the beginning, if you take a look at the heat budget equation, in fact, you don't really have to retain the full heat budget equation for these increments, that it really reduces to kind of a local storage in most parts of the ocean, except in these strong boundary current regions. And as I say, we think that the 5 watt per meter squared target is doable. And we also find evidence of ocean model errors in looking at the increments. So once we get rid of the error due to the surface heat flux, what's left is a lot of that is model error. And we can also use this procedure for selecting among these bulk formulas. And although I didn't mention it in this talk, you can probably imagine that if you can constrain net surface heat flux and the heat storage in the ocean, you could actually use this kind of procedure to come up with estimates of sea ice thickness, which is a quantity which otherwise is very difficult to constrain. So we can actually constrain estimates of net surface heat flux based strictly on looking at how heat gets stored in the other components of the Earth system. So that's it. Thank you.